Hey, welcome back. Let's make a bunch of parts. I had an order for 3 of these small assemblies here, which consists of this copper screw and this block-like part here that screws together like this. And what it is, it's a desoldering tip for a certain electronic component. So what's really important is basically the whole spacing, the whole diameter, and the rest is not very critical. And what's also important is the geometry of the screw back here, because that's what interfaces into the soldering iron. Means it's really not a high precision part on the outside dimensions. Can be machined fairly quick. I decided to do this on the manual mill and of course manual lathe, because the CNC is currently working on some water pump impellers for Honda motorcycles, and that's a good number of them, and I don't want to tear down this setup currently, so this will be all manual here. This is the first of the parts. This is a small copper screw with a little bit of step feature back here, a wrench flat for a 3mm wrench, M5 thread, and a small step in front here. The back side is surfaced, so it's flat. And to give you an idea how small it is, overall length is 10mm and the thread is M5. The large diameter out here is about 6mm, I think. So let's turn the screw. The material is zirconium copper. That's copper alloyed with zirconium, which makes it a little bit harder and easier to machine. Regular copper that's unalloyed is super soft. Originally, the customer asked me for beryllium copper, but I'm a little bit hesitant of machining beryllium copper because if there is any dust generated in the process, that's rather toxic, and I would prefer not to have that stuff around. So we settled on the zirconia copper. It really machines nice and gives a very nice finish with decent tooling. So let's go to the lathe and see how we make those small little buggers. This is 8mm bar round stock, and we pull a good length, about 14mm out of the chuck. This is a 5C collet chuck, and we pull about 15mm out of the chuck. So we have some space to work here. The first tool we're using is a DCMT insert with a 0.2mm nose radius, which is a polished and ground insert for aluminium. So first we will rough out the contour of the part, all in one pass, just to get roughly to diameter. We will leave 0.25mm in diameter on each feature. So as you can see, we roughed it all down in one pass. Now we do the same contour to find the dimension. This is all done with the DRO without measuring. I measured the first part, and since that was good, I can go with the DRO and just repeat my numbers. Since we thread this section here, we need a thread relief behind it. And a DCMT insert does a very good job on this. Roughed it out, and now we do a second pass, finishing it. So that's all the turning done with this tool. We need a little bit of a 60-degree chamfer back here. We will do that with a threading tool. And also we will pre-cut the thread before we put a die on it. Here we go with the 60-degree threading insert. This is a partial profile thread. It does not cut the OD. Means this can only be used if you have a mating part for your thread. So you can check it, or you use thread wires to check it. If you have a topping insert, you can just thread the part and measure the OD with micrometers, and when you have the correct OD, the thread profile and the fit all will be correct. But since I don't have a 0.8 millimeter pitch topping insert, I'm using this here. And I'm also not going to finish the thread using this, I'm using a die. So first we will do the chamfer that's missing. Pick up my 0 from the end of the part here. This is just done by eye with 10x magnification. For you it doesn't look aligned because of a parallax error, but in reality it is. This insert, since it's a coated universal insert for steel, aluminum, cast iron, whatever, leaves a little bit of a burr in this dead soft copper. Well, it's not that soft. This is already a harder quality of copper compared to pure copper, but still, compared to steel, it's still soft cheese. Now we do our threading. Okay, since this is a non-topping insert, it has no corner radius on its front. Means I would have to cut, the minor diameter is smaller than the actual spec by the ISO standard. Means I would cut into my relief back here. And since I don't want to do that, I'm going to finish the thread with a die. This is my die threading setup on the lathe. This is a boring bar holder. And I have this piece in here, which doesn't allow for rotation, but for length adjustment. And it holds a die in here in different diameters. I have them in all important sizes. And this just goes in the tool post of the lathe and get moved to center. And I'm threading here by moving this manually in and out. Push it up against the section that needs to be threaded, and then I spin the part counterclockwise until I can feel the thread engaging in the die. It will make a little bit of a tunk tunk, a small jump when it passes the thread start. Add a little bit of cutting oil, then we thread away. We could do this under power, which we will. There we go. And that's a fairly nice M5 thread in copper. And we come in with an ultra fine needle file to break some of the corners, or edges in this case. Followed by a piece of Kratex rubber abrasive. go. Wash the part with some alcohol. Blow it dry. And we're almost done here on the lathe, but first we have to move the part over to the milling machine and cut the 2 wrench flats. We're using the 5C indexer over here in the milling machine that uses the same 5C collet on my lathe chuck to hold the part and cut the wrench flats. There we go. The collet chuck I'm using to hold this 2mm 2-flute Mitsubishi carbide end mill is a very small diameter and rather long ER11 chuck. I like this because it gives me enough clearance to work close to the collet here. When I move the camera, things get a little bit clearer. We are moving fairly close to the 5C collet here. This small ER11 chuck allows to keep this overhang very, very small. I touched off on the end of the part, moved in the correct distance, and now I just cut the wrench flat. For milling we use a little bit of cutting oil. 1 drop should be enough. Running at 3000 RPM with the small end mill, 2mm diameter 2-flute. First flat cut. Now we index 180 degrees and do the same. As you can see, we cut both of the wrench flats parallel to each other. Let's get it out of this indexer. Back at the lathe, I have a grooving tool that I also use for a small diameter part of. I use a magnifier to roughly line up the right side of the parting insert with the end face of the part. This is not a precision part off here. A little bit less or more doesn't matter because it's facing the back side anyway. And there it is, ready for the next step and the last step. After collet change, we can grab the part on the OD of the thread now, very carefully, because with copper being so soft, we can damage the threads without a problem. That's why I held the part and moved it during clamping, to get minimum clamping pressure here. Let's use the DCMT turning tool to face off the end. That's the first part of this tiny assembly. Came out very nicely. No sharp corners, nice surface finish, good to go. This is the copper screw that we made previously. And here is the second part of this small assembly. Not completely finished yet. I still need to mill 2 radii and some chamfers and also drill and tap the backside. But that's minor work. For now we need to machine this piece here 3 more times. So let's go to the milling machine. I'm holding a 3-shot chuck. That's, by the way, the Chinese 100mm 3-shot chuck that I made years ago a video about. And people gave me a lot of crap about buying a super cheap chuck and putting work into it. But I have to tell you, this chuck has been very good for me. It was cheap, it does its work, and paid for itself numerous times. I could only get round stock of this copper alloy that we're using. So that's the reason for the 3-shot chuck here. And we extended out of the jaws like 20mm. Clamp it securely in place, and now we can mill all features, almost all features from the first side in one setup. I already used the dial test indicator to center the stock and zeroed out the DRO in the center. So we are doing all dimensioning, all machining off the center of the stock. Means that we do not need much calculations or measuring during this process. The DRO will do all of that for us. For milling, we're using a 6mm 3-flute carbide end mill with a highly polished flute geometry. That's purpose-made for non-ferrous metals, especially softer ones like aluminum or copper. We're running this at 3000 RPM. And in the first step, we just face off the top of the stock, piece of stock. Okay, this gives us the top of our final part. Now we drop down 12mm to machine the 10 by 8.5mm square that forms the body of the part later. Okay, each time I did a finish pass, I moved one direction back and then again. That's a spring pass to make sure that we take out any cutter or machine deflections. So this is now final dimension. Now we can pull the tool back when we machine the small aisle feature here on top. Same procedure again, just on a smaller feature here. That's all the milling on this part with the 6mm end mill, apart from facing the back side. Now we change tools to a 0.7mm carbide drill. Here we are with the 0.7mm drill bit. This is a case where we use a little bit of cutting oil, because otherwise I'm a little bit scared that the copper might gum up the drill bit. To set my depth, I'm going to drill until I see the drill cone transition over in the cylindrical part of the hole, and that's when I zero out the DRO. As usual, magnification is very helpful for this. Well, this works even through the camera. So, well, let's see. Okay, that's too slow. That's about... I drilled far enough in so I get a tiny bit of the cylindrical part of the drill entering into the material, and then I zero out the DRO. And now we can drill 1.8 millimeters deep. I do this by watching the DRO, the C coordinate of the quill, not by looking at the drill bit. The drill bit doesn't tell me anything, and I don't feel anything through the quill of the machine. I can do this only by looking at the DRO and having a very steady hand. Another way to do this would be to use the power down feed of the quill, calculate a good chip load for this drill and a good feed in relation to the spindle speed, and have it drill with power feed. But I'm not that adventurous today. Next position. Now I changed to a inserted chamfer end mill. This is double angle chamfer mill, so you can do also backside chamfering, which we don't need in this case, but it's a nice cutter that's working well, so I'm using it here. And for finding our zero here in the part, we're just using a little bit of blue marker. Now I just need to drop down the cutter until I make contact with the edge of the part. Then I can zero out my C coordinate. Last step is to cut this piece off the stock. I have this tiny flush cutting circular saw. This is a Proxxon miniature table saw blade, 50mm diameter, 1.1mm thick, with carbide tips, and it's just bolted with 3 countersunk screws onto an arbor. I drilled and countersunk the blade myself, but this is not ideal. This blade is very thin and tends to vibrate and create a lot of harmonics, but here for cutting copper it will do fine. And we're just touching off on this underside here. Since we milled the overall height to 12mm and the saw blade is 1.1mm thick, when I touch off on here I still have enough stock left on the part to finish it later. So just bring it half decent in contact, just by eyeball. We're going to run this at 1000 RPM and just walk our way through there. Obviously I'm not cutting all the way through because I don't want to fling the part all across the shop. Just leave a little bit of a tab and break it off. That's a little bit much. There we go. So here we go, without any deburring yet, but that's all coming later. That's my setup to round over the ends of this stepped feature up here. I have my rotary table bolted to the machine, and instead of taking off the vices of the mill, which I absolutely dislike, there has to be a very, very good reason to do that, and just putting on the small rotary table is not a good reason for that these days, because time is money, said the guy who does manual machining here. And I have a ground carbide tip here in the spindle to rough align the work with the center of the spindle, which I first centered on the rotary table. I will bring the camera in a little bit closer so you can see the setup of the part on the rotary table. I have my small grinding vise here on the rotary table, held down with 2 clamps. I have a stop block here, so when I slide the part in, I have a reference stop. And the radius we're cutting is concentric to the small hole here in this part, so I just need to use this pointer here to rough align the part with the center of rotation. And when I spin the part now, this hole is moving concentric to the rotation of the rotary table. But this is not accurate enough for a clean result. I will put a pin in there and use dial test indicator to final align it. Here is my 0.7mm gauge pin. Gauge pins this small are usually slightly bent. They are not really straight. That means that we have to indicate fairly low, fairly close to the hole. And now we can indicate by spinning the rotary table. Now we get this hole really concentric to the center of the rotary table. I used a rawhide mallet to bump the vise around on the rotary table until I get a pretty decent total indicated reading of pretty much 10 micron. Now we can clamp it down. And now when we change parts, all I have to do is pull the part out, put the next part in, move it up against the stop, and I'm already there at the right location. Let's get this out of the way, pull the pin, remove our indicator, and now we have to find a proper end mill, and we can swing our radius here. You saw me do the first part like this. Works relatively well. Put the part in. Make sure it's seated down on the vise and also against my stop block. Clamp it. And I'm not using the, I think this is 90:1 gear ratio. I'm just spinning the rotary table by hand here. And looking at the dial, at the graduated ring down here, so I don't over travel. I keep 5 degrees shy of going full parallel to the travel, just so I don't gouge into the sidewalls. Wouldn't matter really, but it looks ugly, so we're not doing that. Drop the cutter down. And the trick is now, we drop the cutter down, hold the table in hand, spin it 170 degrees, 180 minus 5 degree safety on both sides, and then we retract the tool. Flip the part 180, do the same again, done. Very easy, very fast. Very old school way of doing it too. But that's a tendency with things that I do, it seems. And it's that easy to cut this radius. Now we flip the part around to the other side and we get a very, very nice blended radius here. I really like this result. Next step is a M5 thread on the back side. Usually that would not be very hard. It's not hard in this case too, but some things to consider. The drawing specs out a flat bottom on this hole because this screw, when it screws in, needs to make face contact here with the bottom of the thread or with the hole to ensure very good thermal conductivity. And the way we do this, we drill with a regular 118-degree twist drill, then we follow up with a flat bottom drill, and then we use a tab that has pretty much all the lead-in ground away, and tap all the way until we bottom out. That's also the reason why the screw here is stepped in front to 4 millimeters, so the remaining little bit of lead out of the tab does not interfere with the thread, so we can truly bottom it out. When we take the dimensions of the drawing and calculate how much the screw should stick out, the whole assembly should have a total length of 14.2 millimeters, considering some tolerances being about 0.03 millimeters oversize. I hit that pretty good. It also feels very much like I'm bottoming out. So let's do this, and last step will be to do the chamfers on the sides. So here we are at the milling machine. I have two parallels here, spread apart with a spring so they don't fall over. Part goes in, up against the stop here, clamped in place. Tap down very carefully. This is a rawhide mallet. This is soft enough so with some care we don't damage the copper. We start with a spotting drill. Followed by a 4.2 millimeter drill. To make sure we don't drill too deep, we touch off. This is a 4 millimeter gauge block, trash gauge block, scrap gauge block. Drop the drill onto the gauge block. It's a 4 millimeter gauge block. I enter 4 millimeter in the DRO, and that means when I move the quill down to C0, my drill tip is exactly at the height of the part now. Now I drill my 5.8 millimeters. Then I have a 4.2 millimeter flat bottoming drill. And before we touch off here, we remove the burr from the top of the part with a fine file. Copper is so soft, a regular drill tends to pull up a little bit of a burr onto the surface, which in steel rarely happens. So, same story again, we use the gauge block to touch off with the flat bottoming drill. Punch in our number. Flat bottoming drill tends to chatter a little bit, so we're running this at 500 RPM. A little bit of cutting oil. Now we drop it down to 5.8 millimeters. There we go. Didn't remove much material. Countersink. go. Then I have a spiral flute tab that I removed most of the lead-in and the tip that's used for centering the tool when grinding it. That's just done on the D-bit grinder, grinding it off square. Could also do this on a bench grinder with a little bit of help by a V-block. So we use cutting off. And again, I want to see where I am at, so I'm touching off again on the gauge block. So I'm sure that I bottom it out completely. And since I'm not very adventurous today, I'm going to hand tap this. Just by following with the quill and spinning it by hand. We can unwind it with machine power. Little in-situation inspection. This should stick out. When I screw it in completely, the screw should stick out about 4.2 millimeters, so I can just touch it with the tab, and we're pretty good. So 4.22, 4.2 is target dimension. Good to go. That's a quick way to do in-machine inspection in this case. You saw me chamfer all the remaining edges, and I just flipped the parts around in the vise and tried to use as little movements of the mill as possible. In this setup, when I held it like this, you saw me go X and Y, because I couldn't hold it like this, because of the feature on the underside. This would interfere with the parallels. So I set up a stop here and walked my way in XY around it. I'm using isopropylene alcohol in this case as a coolant and lubricant, because I don't want to deal with the fine chips and cutting oil when I do change my setup that often and that quickly. The isopropylene alcohol blows completely off with compressed air and leaves a dry vise and parallels without any chips on it. That's the reason for it. And in this case, it's good enough of a lubricant. Yes, any liquid is a lubricant, even just plain water, or in this case alcohol. It's good enough to prevent chip welding on the copper, and that's all I'm looking for. This inserted cutter here needs a little bit help in soft materials, but apart from that, it works really nice because it has a fairly large diameter, and that results in a fairly high surface speed, which we like. I hope you enjoyed this. They need a little bit of deburring now with a needle file, but apart from that, they are done. They screw together very nicely with this copper screw here. And I have to say, copper is not the most fun material, but the result in copper is always kind of nice. It looks fancy. So I hope you enjoyed. I hope you kind of learned something. Thank you all for watching, and I'll be back.